tensor networks and quantum algorithms.
Good morning. And yeah, I'm glad to be here. So I think the main goal for me for this period of time is to just sort of share a perspective, which is just sort of a point of view that has sort of definitely shaped the way I think about things. And it basically boils down to this, which is that quantum computation is the same thing as approximating tensor networks. And by the same thing, I really mean the same thing. There's an equivalence between them. To make that sort of very explicit, which I'll do later, I have to tell you what level of which I'm approximating. But that's the basic picture, and this is sort of, it has certainly helped me in a lot of ways to sort of think about problems differently and sort of understand quantum mechanics, which I don't pretend to understand, and all those sorts of things. So, and to sort of, so this is the result, but it kind of leads to a point of view, which I think most of you actually already have in either implicit or explicit ways, but that the time in a sort of quantum computation setting is really just geometry, or I can sort of replace it by geometry. And this idea of a unitary map, or unitary evolution, really gets replaced just by linear maps. And the other part of this perspective that at least I find helpful is that it kind of provides a sort of unifying platform to sort of think about these quantum questions and also think about classical simulation. And I'll try to touch upon that. And all of I think most of these things, elements of them, have been seen in various talks this week. And I wouldn't be surprised if a lot of you come away from this saying, oh yeah, I knew that. So, but we'll see. So let's see. Okay, so and I'm going to sort of finish off with an open question that I've had for quite a while, that at least in this picture is certainly interesting for me, and I think it might be something that some of you may have something to say about. So that's the plan. So let's see. I'm going to just start by sort of saying what I mean by tensors and by tensor networks, just so that we're all on the same page. So I think we can probably go through this quickly, but of course, definitely stop me if something seems wrong or not quite your intuition or not quite how you're used to thinking about it. So for me, a tensor is going to be a picture like this. Okay, so it's a sort of blob, maybe it's a labeled blob, with some edges coming out of them, right? And the edges take on labels. So each edge can be labeled, and we're thinking of the labels as a basis for a standard basis for some dimensional space. So I'll even use this notation for the labels, right? And then if I actually label everybody, anytime for any set of labels that I label anybody, if I label all the edges by something, spits out a number. 0.7, for example. Right? So, okay, everybody knows tensors in a different ways. One way to say this is it's an array of numbers. It's a multi-dimensional array. There are various other things. This is just an encoding of that statement. All right? So as long as I label all the edges, the thing that pops out is a number. So So that's a tensor, and the value of sort of writing it as a picture is that you can simultaneously view it as different interpretations. So the one interpretation is as a vector. And so for simplicity, for now, I'm going to say, I guess, that there are D labels, and I'm going to have every edge have D labels. But in general, you could have different edges being allowed to contain different numbers of labels. But if it was D labels, then M I could view this tensor M as a vector in where? Well, in CD, each one of these edges tensored however many times the degree is, which is, in this case, 1, 2, 3, 4, 5. Okay? And what is the vector that it is? Well, I just write out in the standard basis, and the coefficient I put in front of I1, I2, up to I5 is what I would get if I labeled the first edge. I pick some ordering of the edges. If I label the first edge by I1, the second by I2, the third by I3, the fourth by I4. Okay. And so what I would stick here would be in the 0, 2, 2, 4, 3 coefficient would be 0.7. Okay, but the point of this is that also there are other interpretations for this tensor, and the other interpretations are as a whole number of linear maps. Okay, and as linear maps, what I'm going to do is I'm going to interpret. I'm going to split the edges into two sets. Okay, so suppose I sort of single out these two edges. Right. And in this case, if I've singled out these two edges, I'm going to view M as a map from 2 copies of C to the remaining 3 copies of C. D, sorry, C to the D, this sort of local space. And how am I going to define this map? Well, if I can tell you what it does on a basis element of CD, so I'm going to tell you what it does on I1, I2. Well, it's going to send it to some sum over I3, I4, I5. Okay. And what's the coefficient here going to be? Well, you guessed it, right? It's going to be, I label these 2 edges by I1, I2, these 3 by I3, I4, I5, out pops the number again, right? And so in this case, the component of 0, 3, an M takes 0, 3 to a sum of all kinds of things, and the component in the 2, 2, 4 thing is going to be 0.7. Okay, now so this sort of, so you may have seen tensors in different forms where you talk about covariant and contravariant sort of pieces to them, which means sort of you kind of specify which are the input edges and which are the output edges, and then you worry about conjugation and things like that. I'm not going to do any of that. I'm going to sort of, it's not really sweeping it under the rug. This is going to be my convention. This is how I'm going to interpret things. And so if you do want to make covariant and contravariant, you may have to take conjugates here and there to do what you need to do. Okay, is that clear so far? Okay, so I've got tensors, and what are they good for? Well, I want to sort of manipulate them, right? And so I want to do various operations on these individual pictures. Right? And I want to sort of understand what I'm going to sort of draw new pictures from old pictures, and I want to make sure we all know what they mean. And so there are just only 2 operations. The first is that I can stick 2 different tensors on the same picture. All right. So this is maybe one tensor, and this is another tensor. And what I'm going to tell you is that I'm going to interpret this as a third tensor, and the way I'm going to do it is I'm just going to, instead of using this little black circle and that black circle, I'm going to sort of take a bigger circle like that, and I'm going to view it as something with 7 edges coming out. And now I have to, if I'm going to view this as a tensor, I have to tell you what number comes out when I label all these guys. So if I label all these guys, I go back to this picture that has all these guys labeled, which means this represents a number and this represents a number. And the number I'm going to associate with this guy is the product of the two. Okay, pretty simple. Okay, and what does this correspond to? Well, when I'm talking about, when I think of these individual guys as vectors, this corresponds to tensor product. Okay. So this is tensor product when tensors are thought of as vectors. Okay, so that's this operation product. And then there's a second operation, which is contraction. Okay, and the second operation, so again, I'm going to sort of give you a picture, and I'm going to tell you how to interpret that picture as a tensor. So let's say I have this guy again, and this guy. But now what I'm going to do is I'm going to join two of the edges. Okay, so M and N. Okay, so now if I do my same thing of sort of drawing a little box, that a little bulb that encapsulates all the stuff that doesn't have stuff, and make sure everything still has stuff coming out, what I see it as is a picture with, well, 5 things coming out. All right, so I want to view this as a tensor. So what do I need to do is, if you label all these guys, I have to tell you what number should come out. Right? So label all these guys. What happens? Well, we get all these guys labeled, but we don't get this guy labeled, right? If I specify a label here, that gets everything here, right? And what I say that this is equal to is the sum over all possible labels of this guy. Okay? So if for any particular labeling of this guy, now everything's labeled, okay? And I've got one number here, one number here. I multiply those two numbers together, right? And then I sum over all possible labelings of this internal guy. Right? And so this is contraction, and so this is another way of taking two tensors and producing a third one. Okay, so with this setup, right, now there's meaning to pictures like this. They don't need to be planar. Hopefully I didn't. And then if this would be M and P, etc. Okay. So, and maybe I have some edges coming out. Maybe I don't. Okay. Any picture like that has meaning, right? Because it's how did I get such a picture like that? Well, there are many different ways I could have gotten it using these two operations, depending on the order, right? One way is I could have plopped down each of these guys as individual guys first, and then started joining things up. Another way is I could have just plopped down the first two guys, joined them up the way they wanted, plop down the second one, join those. But the beauty of sort of this notation is that it doesn't matter what order I do it. If you do the calculation as to what it is that this is supposed to mean, it all means the same thing. And if you want to figure out what it means, is you draw a big circle around the whole thing. That gives you that it's some sort of tensor, depending on how many lines are coming out of the circle, how many free edges there are. As soon as you label the free edges, you have to tell me what number comes out. And what number comes out is a sum over all possible internal labelings. Right? So it's a massive sum now, right? It's a sum over, you sum over all possible internal labelings. For each internal set of labelings, right, there's a number pops out for each of these tensors. You multiply those numbers together, and then you do this massive sum. Okay, so encapsulated in this kind of network is a massive sum, right? A sum of how many terms? Well, it's exponential in it's d to the power of the number of non-free edges. Sure. Okay, so, all right, so I'm probably not hitting anything that you haven't thought about in some way or another. Oh, this is an interesting feature of having a hole in your pocket. What? Maybe like this. What do you think? We'll see what happens. All right. That's it. That's it. The number of free strands coming out of my pocket. Okay. So okay, so this is basically, so the way I think of this is basically a graphical sort of picture of linear algebra. And so this is sort of, there's various familiar things, and so for, I guess everybody knows this, but I'll sort of do it anyway. So a picture like this, right? I want to sort of have a picture of what that means in sort of the world that I'm used to living in, which may not be tensor networks, right? So a picture like this turns out, if you sort of figure out what it is, it's the sum over this. So what if I interpret m as a vector and n as a vector, right? This becomes the inner product of m and n. And maybe you have to put a conjugate on one of them. Okay? Right? Because I sum over internal labelings, and then I have a product of things. So this is an inner product. And so would a picture like this. If I had two guys, and they're joined up by many strands, still same picture, right? I can sort of take this, break it in two. I can think of the bottom as a vector, the top as a vector, and the thing as an inner product. Right? And this is not sort of vague schematic, like, you know, things. This is precise, right? This is actually the inner product when you think of these things as vectors. Okay, and so now we've also got, you know, maybe a picture like this, and I want to sort of, this is sort of the classic contraction picture. Okay, and I can sort of say, well, how do I understand this tensor? Well, let me think of M as a map from here to here, a linear map or a matrix from here to here. Okay, and I'll think of N as a matrix from here to here. Right? Then what this picture turns out to be is matrix product, right? This is the composition of two linear maps. This is the map M followed by, depending on whether you have left or right, whichever way, M times N. This is M times N. Okay, and so more complicated pictures, right? They do that, and then like that, and then have a sort of picture like this going on.
But this doesn't specify the dimensions.
This, I haven't specified the dimensions.
So the picture is not exactly isomorphic to linear, because you don't know the sizes. You just know the order of the products.
Well, so let's see. So if we imagine that each of these edges has a thickness associated to it, that would be fine.
Thickness.
Like meaning the number of labels it absorbs.
But there are also these loose ends, right?
Yeah, so this would be a map from whatever dimension space this is to whatever dimension space that is. Okay. And so all we make sure is, so maybe I should say that, so though I was restricting to the case where they're all the same dimension, if I change the dimensions, then in my contraction setup, I have to make sure that I only join things that are at the same dimensions. Okay, and so a picture like this, right, if I sort of cut it here, I can see the top part of the picture as a tensor, right? But I'll think of it as a linear map from these guys to these guys, and the bottom guy is a linear map from these guys to these guys, and this is composition of those two linear maps. Okay. Okay, and so with this point of view, now this takes on much more rich meaning, right? So I can think of this. This is a tensor, right? This is a tensor, okay? But I can think of it as being formed by some series of operations consisting of linear maps or inner products or various other things. Yeah?
So how would you represent the trace of the product?
Good question. Good question. So you're not a plant, are you? Okay. So not a plant. Okay. For the non-native plant, meaning some, a magician plant, somebody in the audience to, not the growing type of plant. Okay, so actually let's start first by saying what's the trace. So if I have M as a matrix, M is a tensor, but I'm going to interpret it as a matrix. Let's pretend these guys have the same dimension. How do I write down the trace of that matrix? Well, that's just the sum of the diagonal elements. I want the top guy to be the same as the bottom guy, and so the way I do that is this. Right? So this is the trace of M. Okay? So the trace of a product looks like this. And now, I don't know, this is the best proof I know of the trace of Mn equaling the trace of Mn. Right? Because once you have this, right, what do? You take this guy, you bring it down, you bring it around. Now it's an N but it's upside down once it's over here. Like that, right? Which looks like a U, I guess. And then you keep going, it's up here, now it's on its side, and you, by the time you're done, you get it up here, and it's back to its normal position, right? And now I interpret this picture, and this is the trace of NN.
But if you stretch the right leg, the long leg, and make
This
it
one?
Yeah, the one that goes around.
Yeah?
You can form a picture that looks like a rank 2 contraction of tensors.
Let's see, rank 2 contraction. So what are we going to do here? So go ahead.
Actually, that's
What did you want to do?
what are they some of, I mean,
So let me repeat it, but I think it's okay. So if you have this N and M have an edge, right?
Yeah, they have two
M and N,
edges. Okay.
M and N have an edge.
Here's N and here's M.
Yeah. Then you have another edge that's not straight, but also connects M and N.
This one.
Yeah.
Mhm.
But you can make it straight, and it looks like a rank 2 contraction, right? Looking at the top right picture you have, top right. So yeah, if you erase one of
Yeah.
those edges, it'll look identical.
that's basically.
Yeah. So you could rewrite this as this picture. Is this what you're trying to say? And that picture. Is that what you're trying to? Is that what you're saying? And then we could sort of think of it as.
So all I'm saying is that the right-hand top, you know, if you delete one of those edges where your finger is, it's the same picture.
Yeah.
That's all I'm saying.
Okay. Yeah, and that's true. And so
It's
if we
okay.
and
Yeah, it's okay.
that turns out to be the same
Yeah.
relation.
Initially, I thought it wasn't okay. No, sorry.
That's okay. Okay, so, all right, so we're all set with that. Okay, so now what is a tensor network? Well, a tensor network is a picture like this, like the one I drew. Okay, it's just a collection of tensors, some of which are joined, some of which are not. Okay, so a tensor network is a picture like this with lots of tensors and things, and we'll pretty much focus, though not completely. Okay, so actually, so let me just say what a closed tensor network is. So what I'm calling a closed tensor network is a network like that with no free edges. Okay, so everybody's joined to something, right? And so a tensor network, a closed tensor network, has no free edges. And what does that turn out to be? That turns out to be a number. Right? So closed tensor networks are numbered. Open tensor networks, we can interpret them as different tensors. Okay. Okay. So remember, sort of this is where I'm going for, right? Which is that quantum computation is the same as approximating tensor networks. So let me start with a motivating example, which is how to view a quantum computation as a tensor network. Okay, and this is pretty straightforward, but let me do it nonetheless. Okay, so what's a quantum computation, right? So you start by initializing some thing in a set of zeros, let's say. And I'm going to draw a circuit picture of this thing. And now I start to apply some unitary gates. And I do that for a while, applying my unitary gates, local. And eventually, what do is I measure the first qubit, or qubit. Okay, and I see how often I get 0 and how often I get 1, and I use that as my computation. Okay, so I want to view this as a tensor network. So how do I view this as a tensor network? Well, very simply, it's almost there by itself, right? So these guys, I want to think of this initializing in 0. I want to think of as a tensor. So I'm going to define a particular little small tensor that I'll call 0. Actually, I'll call it 0 without the thing on it. 0. Right? And the 0 tensor will be such that if you label this by 0, it spits out a 1. And if you label it by anything else, it spits out a 0. Okay? All right, so here I'm going to start out. So now, at this point, if I lay the same tensor over and over and over again, and I look at what I have right now, I have a vector, and that vector is the all zeros vector, just like I would have had at the beginning of the computation. Right? And now I'm going to apply some unitaries. Well, unitaries, I'm going to write down the tensors that correspond to the unitaries, thinking of the tensors as linear maps. Right? And so these squares become circles, okay, but never mind, right? And by the time I'm done down here, before I've done measurement, right, I have, if I draw my big red picture, if I look at, this is now a network, and if I look at this network, it's got a bunch of edges coming out the bottom, and if I interpret that as a vector, I'm going to have exactly the state I have here before I've measured. Okay. So now if I want to know the probability of, so what do I have here, right? At this point, I have some vector psi. Okay. And I end up writing psi as equal to psi 0 plus psi 1. Right? Where psi 0 is the component of psi that has 0 as its first. Right? So if I write psi, well, maybe I'll do it this way. Like this. Okay, so this is, I decompose psi into its piece with 0 in the first coordinate and its piece with 1. I'm now assuming these are qubits. Okay, and my probability of getting 0 is what? It's the absolute value, it's the norm of square root of psi 0. That's the probability of getting 0, my outcome being 0. Right? So when I do a computation, right, and I do it maybe multiple times or I do it once, right, what do I get out? I get out a sample from the distribution psi 0 squared and psi 1 squared. Right? So I get an approximation for this value. If I do it multiple times, I get a better approximation. Right? Well, right now I've got this vector psi right here. Okay.
I don't understand. You have 0 and 1 next to psi 0.
Yeah. So psi 0 and psi 1 live on they live on this space.
Okay.
And I just decomposed it in terms of within as a.
Yeah. But then the probability you said is the norm of that vector.
Norm squared. Yeah. So the probability that if I measure the first qubit, right, the probability of it showing up 0 is the norm of this vector squared. Right? This is an orthogonal composition. The sum of the squares is 1, and the probability of measuring 0 will show up with probability of the size of this thing squared. 1 will show up with the size of this thing squared. Okay. Okay. So this is the number that the computation sort of approximates, or 1 minus that number, whichever way you want to do. And right now I'm sitting here at psi. Okay. So now if I just add the tensor, if I put in the tensor 0 down here, what does that tensor do? That tensor just sort of picks out psi 0. And if I put this here, the resulting thing, so before I had psi coming out, right, I had something that looked like psi. And now I put a 0 here, the 0 tensor. What's left, I'll leave you to verify, that this picture is equal to psi 0. Okay. So this is psi 0. How can I write down a picture that gets me the norm squared of psi 0? Well, it's a vector. I want its norm squared. I inner product with itself. Right? So what do I want to do is I want to take this whole picture, pick it up, turn it over, put it in conjugates, and put it on itself. So let me not draw that, but draw some schematic version of that. these zeros. Then I'm going to sort of encode the rest of the circuit by some C. Then I stick in this 0 here. What I'm left with is what I called size 0. Now I'm going to pick that picture up, turn it over, and inner product it with itself. Okay? And what do I get out of this? I get exactly out the probability of showing up 0. Right? This is equal to the probability of measuring 0 in the first. Keep it. Okay? Okay, so here's the tensor network that encodes the quantum computation. Right? So what have I done so far? I've showed that any quantum computation can be seen as approximating a particular tensor network. Right? And what's the form of this tensor network? Well, you start out, and then you use unitaries, and then maybe you're allowed one projection right at the end. Right? So it seems like a very specific class. Right? But what I'm now going to show you is that, in fact, let's not worry about its structure, because we can reverse this process as long as we define what we mean by approximating. Okay, and let me just sort of say quickly what I mean by approximating here. If you want to approximate, one time doing this, right, just gives you a sample from a distribution that's weighted size 0 squared, psi 1 squared. If I'm allowed to do this polynomial number of times, I get a polynomial approximation to this guy. Right? So what is the value of this tensor network is exactly psi 0 squared, and what does the quantum computation does? It gives me an approximation up to 1 over a poly of that value.
And it's additive approximation
In
here.
this case, it's yeah. I guess there's no.
There's no approximation.
No. What Tomas was saying is that the quantum thing gives an additive approximation to this number.
If you sample it,
Sampling is an additive, which I guess needs to be stressed for what happens later. Okay, so now, okay, so what do we want to do? We want to take this as inspiration, right, to do the reverse. And what's the reverse, right? The reverse is starting with any network. Right? And designing a quantum algorithm for computing its value. And okay, so what are the components that are needed? So quantum algorithm or approximating tensor network. Okay. So the first thing I'm going to do is I'm going to pick up what we'll call a bubbling, which is just an ordering of the tensors. Okay, so I'm going to pick an ordering of the tensors. So let me pick this ordering. This is the first, this is the second, this is the third, this is the fourth, this is the fifth, this is the sixth, this is the seventh.
Zeph, is there going to be some norm constraints or something? I mean,
Yeah. No, I mean, the approximation is going to absorb the norm constraints. Yeah. Okay, so what do I want to do is I'm going to, here's the idea of what bubbling looks like. Bubbling is, I'm going to imagine that I have this bubble that starts to swallow the network. Okay, so it's like this big red blob, and at first it comes on the outside, and the first thing it's going to do is it's going to swallow this. That's the first vertex. The second thing it's going to do is it's going to move over here, and it's going to swallow that. So that's what a bubbling looks like. And that sort of gives you a sort of picture of how I'm going to interpret each of these tensors. Right? So the first tensor that it swallows, I'm going to interpret just that as the easiest way to think of it is that that's some vector that I'm starting out with. Okay? And then the next one is going to be like this. Okay? And what I'm going to do is to say how I got from here to here, I'm going to interpret this. I'm going to now use my tensor network interpretation to say, you know what? I'm going to get from here to here by applying this tensor, but as a linear map from the guys that are touched beforehand, which is this one, to all the ones that are touched by the time I'm done, which are these three. So I'm going to view this tensor as a linear map from the ones touched before to the ones that weren't touched before. Right? And I'm going to keep going. So now for 3, I'm going to view it as a linear map from these two, because these two have already been touched, to the following 3, et cetera, et cetera. So what I'm going to first do is sort of see this map as a sequence of events, which is starting with a vector, then applying linear maps. And if you'd like, the last one can either be inner product with another vector or applying the linear map that's, let's not worry about the last one next, because I'm just going to be tangled up with words.
So are you assuming some kind of bounding degree for each node or something?
Yeah. So let's keep. So yeah. So that's a good point. So the tensor network, I should have said let's say every tensor has bounded degree of some size. Constant degree, I guess, would be helpful for what I'm going to say.
But you could always do some kind of Schmidt decomposition to arrive at if you didn't.
Yeah, you could. Though you might worry that different Schmidt compositions would give different levels of approximation. Yeah, but yes, you could. You could. As long as you had the ability to do that in time that you have. Okay. All right, so now, so do people see sort of what I'm trying to do is I'm trying to sort of the vector that I'm starting with, I'm going to try to make it look like this, and then the linear maps, I'm going to try to do this stuff. Now, you'll notice something important, which is those linear maps all need to be unitary, right? There's no need for any of these maps to be unitary, right? Okay. So there are two things I have to sort of keep track of. So this is these are not unitary, these maneuvers, right? So let's talk about any particular map. So does everybody understand the sequence of events? Once I bubbled the thing, I can sort of see it as starting with a vector and moving by linear maps to the end. And the result of that computation, whatever that is, that's the value of the tensor network. Right? And so now I'm going to sort of, so let's sort of look at any one of these maps. Let's look at this map A. Right? So this A is not necessarily unitary. So let's deal with the first problem, which is that it may have operator norm greater than 1. Okay. But I can compute what its operator norm is. It's a small tensor, right? So what I'm going to do is I'm going to keep that information on the side. So I'm going to replace A with A over the norm of A. And in doing so, I've now at least made A norm 1. It's not unitary, but it's norm 1. Okay? And I'm going to keep track of, I'm going to hold on the side all those A's. So I'm going to keep track over here. Okay? The product of the norms of all the A's. Okay, so now I'm going to pretend that actually the picture that I had was A over norm A, which had norm 1. Okay? And by the time I'm done, I know that I have to scale everything back up by this much. Right? So I'm going to sort of, instead of doing this tensor network, I'm going to do the normalized version of this network. I'm going to replace every tensor by it over its norm when I was thinking of it in this particular ordering. And I'm going to approximate that one. And if I get an approximation of that one, that will translate once I scale to an approximation of the other one, because they're related by just this factor. Okay, but I still got a problem, which is A has norm less than or equal to 1 now, or actually equal to 1, right? But it's not unitary. Right? So what do I do about that? Well, I do something pretty simple and standard, which is I embed it in a unitary that's slightly bigger. Okay. So there's, so if I started with an A. Let's now pretend that A is normalized already. So if you look at this map, let's get the this is unitary. So for any norm less than or equal to one thing, if you sort of form this slightly bigger matrix, or however you want to map, right, that's unitary. And this is just akin to saying, just think of this as if you had a real number that was less than 1, and you wanted to sort of put it as the upper left-hand corner of a unitary, you'd just use a rotation where that number sat in the upper left-hand corner, right? So this is like sine, cosine, minus cosine, sine. This is the exact same thing. It's just done in operator. All right? And so pictorially, what this is saying is, notice that the upper left-hand corner of this thing is A. And so pictorially, this is this fact that if I take U, which now has two indices, on top and bottom, and I restrict by putting a 0 here and a 0 here, which says, if I do that, if I put those tensors on the end, what am I doing? I'm picking out the top left corner, right? So this picture equals this. Pictorially, this is what it is. It's that any operator of norm less than or equal to 1 can be written as a unitary on one more qubit, where I now squeeze that extra index by 0. Okay, so now I'm in good shape, right? Because I was complaining before that these operators are not unitary. Well, I can throw in an extra, I can put in a picture like this. Instead of a picture like that, I put in a picture like that. And so now what do I have is I have the same picture as the old, but I've got some guys sticking, there's some zeros on the top and the bottom. I pick up all the zeros that go up towards the top. And so this picture, which before let's call it T, right? Once I make this transformation, it looks like a sort of T prime with a bunch of zeros sticking up and down. And let me yank them, all the ones that were going up, up, and all the ones down, down. Okay? And what I've got left inside is a unitary evolution. Okay? So now I can actually do this with a quantum circuit. Right? And all I'm left, so I've now got this sort of vector, so I can evolve up until here. And the only thing I have left to do is finally, with my, so far I've done by a quantum computer, I've evolved to have this. There's a tensor right down here, and I have that tensor in my hand. I want to inner product it with the all zeros vector. Right? And there's this, involving the swap test, this is a simple thing to do. So there's a unitary, there's a quantum algorithm for taking a vector and inner producting it with the all zeros vector. It's very simple. And I think I'll just sweep that under the rug for the moment. It's not worth spending time on. So let's see what I've got after all I'm done, right? What I got, once I do this quantum thing, is an approximation, right? So now my quantum algorithm, what happens is I have success in the quantum algorithm exactly proportional to the value of this network. Right? But the value of this network, right, was a scaled version of the value of the original network. Right? So what I got was a quantum algorithm that approximated. So this is my quantum algorithm. It came up with a value, which is its success probability. And this is a 1 over polynomial approximation to not the original tensor network, but the tensor network over delta, where delta was the side factor of keeping track of all these norms. Okay? And so what this means is now if I sort of multiply through by delta, right, I can give an approximation. I use my value of q, I multiply it by delta, t minus that as an approximation at the approximation level delta times delta over poly n. Right? So that's, for delta, if I'm pulling out a factor of 2 every time, that's a pretty poor approximation. Right? Sort of, it's 1 over poly times 2 to the n. Okay. Well, it is what it is, right? And it turns out that not only is it a poor approximation, but it's the best that a quantum computer can do, and it's all that a quantum computer can do. This is a complete problem, as stated. Right? So even though that level of approximation isn't particularly impressive, it's all you can hope for out of the power of quantum computation. Sure. Yeah. Okay, so you may ask, so there's certain questions to ask, and then let me just sort of touch on how this point of view sort of shapes other things. So the first thing to sort of point out is bubbling does matter. Okay? I can choose one bubbling and I get one delta. I can choose another bubbling and I get a different delta. Okay? So bubbling does matter. Okay? And finding the best bubbling is provably hard. So if you're trying to do this if you're trying to design this for a certain thing, you want to use heuristics to try to find good bubblings. The second thing to say,
Sorry, you said hard? How hard?
I think it's at least, it's NP-hard.
It's NP-hard.
Yeah,
It's NP-hard.
that's
So
NP-hard.
that's because that's in the slight, I mean, it's bubbling in the sense of minimizing the product of the norms.
Yeah.
Right? So it's,
So the other thing that you can try to do is take this tensor network and replace it by a comparable one. Right? I could sort of say, well, maybe there's a decomposition of this map in a clever way that sort of, now I've split this tensor into two tensors in an interesting way, and that does yield some success. You can hope to do that and improve your levels of approximation. I should have said at the beginning of this is work with Itai Arad. And now let me sort of touch on where this goes. So with this point of view, here's what happens. So this point of view sort of basically says, look, any problem that sort of has a graphical picture associated to it is something that I can sort of now do a quantum algorithm for. And I'll get some level of approximation. And that's exactly what was done with the various, I don't know, I guess some people call them sort of these topological quantum algorithms, I don't know. But anyway, so there's these quantum algorithms for approximating the Jones polynomial or the Tut polynomial, and there's some quantum field theory stuff. So all these things, this is the framework you should see all those in. Right? All these, they take these objects, and there's some way of looking at them for which these guys aren't too bad. And that's the whole picture. So for the Jones polynomial, for instance, for those of you who don't know, it's a sort of topological, if you have a braid and you want to understand whether two braids are similar, you're looking for invariance of the braid, so the Jones polynomial is such an object. And the way the scheme works is you find a representation of the braid group, right, which means sort of sticking it in as linear algebra. And what that translates to is that you can sort of turn these into tensors. Right? There's a representation for which these are tensors. They're linear, a crossing is a linear map. Right? And now you just figure out the right way to right way to bubble this thing, and you're all set. And the focus on certain roots of unity is because in those cases these things are unitary, these crossings. Okay, so let's see, I'm running out of time, but let me sort of just say, sort of bring us back to this time geometry or unitary linear map. So the unitary linear map is sort of pretty clear. The time geometry one, I just want to sort of say in the following way, right? Which is that I'll just say it as this result, which sort of came at some point, which was sort of surprising, at least at the time, to some people, was that log depth quantum circuits are classically simulatable. I don't even know if simulatable is a word. Okay, so there's sort of a lot of different ways that I think several people realized this at virtually the same time. But here's the picture, right? So let me view the quantum circuit as a tensor network. Okay, and what log depth means is that the number, so I've got this sort of stuff going on. But the amount before I'm done, and then I do a measurement here, I can just sort of say it's between 0. But this is log length, log n. This is length n. So we know that the probability of this involves just sticking this thing and putting it upside down, right? And doing that. So this is the network we're trying to evaluate. Now, how do we do this classically? Okay. Well, quantumly, we were kind of going this way. Classically, we just swallow this network this way. Okay. If you swallow this network this way, and you sort of start to bubble it this way, think of what, at any stage, what a bubbling line, how many free edges a bubbling line crosses. And how many things are sticking out here? You have to kind of weave your way around these. The only place where you're sort of going to see a crossing, right, is, sorry, I should have been here. Right, so as I come down this, the only place I have to sort of move out of the way is when there's an actual operator sitting right here. Right? And then I kind of have to bump out of the way and I hit two edges. So the number of edges that are going to be sort of cut by this line is just twice, at most twice log n. Okay? So what I'm looking at is trying to keep track of a tensor with twice log n edges coming out. Right? Each of these are dimension d. What size space is this? This is size space d to the log n, or d to the 2 log n, right? Which is a polynomial size space. I can do that classically. Just do it. Keep track of the thing, and now I do linear algebra on this polynomial size space. I keep sort of edging my way across, pushing things so that it's pretty much upright. Right? And by the time I'm done, I'm done. I'm away at the end, so I'm back to a number. The number is the value of this tensor. It's the exact, right? So log depth quantum circuits, classically, I can compute exactly. Right? And it's the same reason why it points out the same thing that goes on with matrix product states that makes 1D so different from 2D, right? Is matrix product states, there's a narrow direction. If I look at what's going on when I'm doing linear algebra, there's a narrow direction. For 2D, there's no narrow direction anymore, right? So if I have a matrix, if I want to compute the inner product of two matrix product states, right? All I do is, classically, I swallow it this way. I mean, there are slightly more efficient ways to do it if you want to program it up. But this is the spirit of what's happening, right? I'm going across this way instead of coming down that way. Right? In 2D, this is for PEPs, right, where you've got a sort of 2D lattice. And you're doing inner products of two different PEPs. There's no longer such, so now you've got sort of two combs that are sitting on top of each other. Now you can't sweep through it in any way so that it's narrow in one direction. It's not narrow. Right? No matter how you sweep over it, you take a cut in the middle, you're going to cross at least n things. Now you're into exponential realm.
Is your circuit physically local or?
Yeah, this log n depth local circuit.
Physically local.
Physically local, meaning neighboring bit. Yeah, that's important. Okay, so I have time just to say my open question. Okay, so here's my open question. Suppose I give you a tensor network that I want to approximate. With the condition that all the tensors in the tensor network, okay, so here's the extra condition I'm going to put. All the tensors have non-negative entries. Okay? So each one of these tensors is an array. It's all non-negative numbers. Now the question is so quantumly we have an algorithm, right? It's specified this way. It's just an example of a tensor network. So quantumly, we know we can approximate it to some level, right? And the question is, what can you do classically? Can you do the same thing? Can you achieve that level of approximation? Now, okay, here's the reason why you should. The reason why you should goes something like this, right? Quantum is all about taking advantage of cancellations. If I look at this tensor network, everything's non-negative. There are no cancellations in this thing, right? None whatsoever. So quantum shouldn't be able to help us on this. Okay, so that's the heuristic argument that says surely you can do this classically. Right? There's some sort of sampling. It should be fine, right? The funny thing is that I haven't been able to do it. That's not funny, but a lot of other people haven't been able to do it, though I can't quite tell their interest. Their interest fades once their first idea doesn't seem to quite work. But the important curiosity about this thing is that the level of approximation quantumly has to do with operator norm. Okay, operator norm of these tensors. If you think of most sampling ideas, classical sampling ideas, it has to do with L1 norm. Right? It has to do with, you sort of make it a stochastic type thing, and you do it. So you would just sort of naively, you would say, where's that connection, right? Because classically, naively, whatever's going to be popping out is L1 norm. Quantumly, what's popping out is L2 norm. We know that there are plenty of examples where those aren't the same thing, right? You view a tensor and you look at its L1 norm and its L2 norm, not the same thing, right? And L2 norm is better. Right? So how are we going to kind of use a classical thing that does this? So there are plenty of people who know more about sampling than I do, and I'm hoping one of them is here and can do this problem because I'm tired of musing about it. Okay, that's it. Thank you.
Questions?
Just maybe to get a better feel for what approximation you want here. So again, it's a little bit delicate if you're just asking infrared approximations, then asking for a meaningful answer here, you really have to tune this to be bounded away from zero. So I just maybe give a feel for where the hard.
It's a good question. I don't really know. I just don't know any.
If I scale everybody down by then I trivialize the problem. So in the quantum case, it's clear what the right scaling is, but now I'm.
So let's perhaps what I do is I sort of give you a order of the bubbling with the requirement that these linear maps in that ordering are norm 1. Now the scaling is fine.
Well, we're just left with the L2 versus L1.
Yeah. And that's not particularly helpful as an answer, right?
I had another quick question. So for these log depth circuits, you said, okay, you can simulate it classically, sort of bubbling the thing from left to right. Another way we know how to do it, of course, is you could have a MPS for the starting state, and then just go down, straight down, and update that MPS as you apply every gate. And you'd end up, because you're only going log times, you'd end up with a polynomial size MPS at the end of the circuit. And there would be another straightforward way to do it. I was wondering how they, there's cases where you could imagine where the one would be much worse than the other.
Oh, I
where
see.
I say,
Yeah. So, but maybe is that maybe sort of thought as a, then eventually you have to. Then to eventually do the MPS, you have to sweep this way. So is that just sort of maybe
for the ultimate contraction? I mean, if you're just interested in starting on 0 and computing the overlap on 0 at the end, then you get an MPS for the end of the circuit, and then you just compute the overlap on 0. Well, yeah.
But
sure.
Isn't that what you have to do at the end? I mean, there's no escaping having to go from left to right.
Well, you take overlap root product state, so you're just plugging in zeros to your input. But sure.
Yeah. So no, I don't know how to.
You can imagine that for one direction, sort of the bond dimension would reach polynomial when the other would not, for certain types of circuits,
Yeah,
where you
sure.
actually really still get a gain.
Yeah, so I haven't thought about it.
Even for cut examples in the case.
Yeah, but you have a.
Well, I mean,
I can imagine you could
there's
make
some physical models. I mean, you have a cellular automata in which there are particles kind of moving freely. If you contract in one direction in tensor network, it's difficult, and the other one is simple.
Well, here, okay, in that particular case, both of them are polynomial, but I guess, okay, one of them could be much better than a polynomial. So you're saying for these.
There are examples in calculus, something like that.
Any other questions? All right, let's thank Zeph. So we have a coffee break and we resume at 11.